Okay. So, we were in the last class we were actually discussing about the click noise. Okay. So, that is something one topic we have started. So, we will not go into the details of it, but let us give you some basic idea of what that click noise is. So, basically we have drawn that phasor diagram, right. So, this is that AC, that is that point, on top of that the noise is being added. Now, the problem is, as long as this noise amplitude is smaller than A, there is no problem, but if the noise starts getting, suppose this is my A and this is the noise amplitude. Okay. Now, what might happen, if this is big enough, this might even go in this direction. So, what is happening to my phase? It was on this direction. Okay. So, the phase, this is the reference phase which is over here, this immediately goes into reverse direction. It might even go into this direction. Okay. So, the phase becomes, so basically there might become a random variation of phase which was not happening over here. Here if it wanders, I know that it will still be remaining on that same around theta. Okay. So, it is not getting a huge variation due to noise. Okay. So, if you just plot that theta, so probably I wish to have a theta variation like this, on top of that there will be small noise induced theta variation. Okay. And I will differentiate it, they will smoothen out even more and I will get my actual message signal variation. Whereas, what will happen over here, once there is a variation and if means if this goes from one particular, suppose it is in this direction, now noise is random. So, it can immediately in the next this one it can go into this direction. So, there will be almost a pi phase shift. Okay. So, there is a possibility now because the noise amplitude is higher. So, there is a possibility that randomly after sometimes suddenly a pi phase shift happens. So, what will that means? This particular thing will have a sudden pi jump. Okay. And then again it will probably track, again another pi jump might be there or it might again come back. So, all these slopes, if you differentiate it, what will happen? They will start creating, suppose after differentiating I was getting this, but this particular point, because there is a sudden thing, there will be a impulse noise which will be created as many pi shifts are happening. Okay. Either in the positive or negative, whatever happens, there will be positive impulse or negative impulse, it depends on what kind of things are there, but whatever it is, there will be a impulse noise which will be coming and they will be coming randomly, because noise characteristics you do not know when it will do that pi shift. Okay. Here even if it does pi shift, my noise due to noise, this variation will not be huge, it will just be a small amount of modulation, but because in the phase there might be a pi phase shift. So, there might be a click noise which will be coming, and this clicks are random in nature. When they will be coming, that depends on noise characteristics. Okay. So, what is the threshold effect? So, this is called click noise. So, basically what you will see that after FM demodulation you will have that original message, which because it has a nice noise cancellation. So, overall noise cancellation will be good. So, the message signal will be smooth, but suddenly there will be impulse and then again smooth, suddenly there will be impulse. So, this will be creating a cracking noise in the receiver. So, whenever you are hearing, there will be cracking noise one after another. This might happen, whoever have listened to FM radio, you might have heard those clicking sounds. Okay. Very rarely happening. But what will happen if the noise amplitude is too high and it remains too high and the noise nature actually varies, this means this arrival of pi phase shift, it happens too often. So, within a second if there are too many clicking sounds, so this particular part, whenever this within a second how many clicking sounds are being heard, if that increases, then that is called the threshold effect in FM. So, at that time probably the message is still being demodulated very nicely, but there are too many impulse on that. So, basically our ear, whenever we hear it, probably that clicking sounds they are too often. So, that will be only reverberating inside our ear. So, we will not be able to hear whatever is actually being transmitted. The message signal will have no consequence, it will be just a collection of clicking sounds one after another coming. So, that is when we say that FM goes into threshold. So, there are analyses that with what SNR value FM goes to means threshold zone, what is the number of clicks in 1 second that will be coming. So, all those things are there. Probably we will not bother ourselves due to time constraint in characterizing those things, but it is good to just know that FM has that kind of effect. Okay. So, it is not all rosy as we have thought. Whenever the signal to noise ratio becomes smaller, so it either goes very close to unity or even less than unity, then we have a big challenge in receiving FM signal. Okay. So, I think with that we have almost finished our discussion of FM. So, whatever we wanted to discuss about FM, we have finished that. Now, we are in a position to actually compare FM and AM with their full scale. So, what is the bandwidth efficiency, what is the corresponding noise characteristics or noise cancellation characteristics, how it behaves in terms of nonlinear channel characteristics, what kind of interference cancellation technique they can employ. So, all those things already has been evaluated. Okay. So, now we will probably start with another form of analog modulation. It is still being called analog modulation because that was probably the transition phase between analog and digital transmission. So, we will try to cover also that that particular analog form of means modulation technique which is called pulse modulation technique. We have already mentioned it in the beginning of our course. So, today we will try to means it is called pulse modulation. Okay. So, this is something we will try to cover. But to understand pulse modulation, we will have to probably start appreciating some of the fundamentals of this pulse modulation or some of the signal aspect or signal theoretic aspect of this pulse modulation. So, that is something which we will be doing first, means dealing with them, and then we will come to the fundamentals of pulse modulation. Okay. So, pulse modulation has 3 types like AM, FM, they had or AM and angle modulation, amplitude and angle modulation, they had their own types. Like for angle modulation we had PM and FM, like amplitude modulation we had means amplitude modulation without means suppressing the carrier, then DSBSC, SSBSC, then vestigial sideband. So, here also there are 3 techniques. So, one is called pulse amplitude modulation, PAM, the other one is called pulse width modulation, and the other one is called pulse position modulation. Okay. So, it is almost analogous to basically frequency, phase and amplitude. Okay. So, if you see PAM, that is actually like this. Whenever we say pulse amplitude modulation, it is in terms of some discrete pulses. So, the entire modulation happens with pulses. Pulse means it is on for some duration and rest of the duration it is off probably. Okay. So, that is generally termed as pulse modulation. So, we will be modulating generally with in terms of this kind of pulse train, which is just these are periodic signal. After every let us say Ts amount of time it repeats and the pulse is on for some amount of time, let us say Tp, and Ts minus Tp time it will be off. So, the modulation happens with these pulses, like we had carrier, we have pulse train over here to do the modulation. So, it almost analogous to the carrier. Okay. And when we say pulse amplitude modulation, that means if I have a signal, this signal will be covered in the envelope of this pulse. So, that means the pulse amplitude will be modulated according to the signal. So, if I have a pulse over here, that will have higher amplitude. Next, if I have a pulse over here, that will have a smaller amplitude. So, it will be just like this. If you take the pulse tip and connect them, they will create the envelope of the signal. So, again there will be a pulse, that will be negative, and so on. Okay. So, if there is a pulse, that will be positive. So, if you just connect the tip, that will just look like the original signal. Okay. So, that is pulse amplitude modulation, whereas pulse width modulation is you now start varying the width of the pulse, okay, according to the amplitude of the signal, message signal. So, basically what will happen if the amplitude is higher, it depends on how you wish to modulate it. So, you can take a decision that if the amplitude is higher, I will have lower width pulse, and if the amplitude is lower, I will have higher width pulse. So, what we will do probably here, if we do pulse width modulation, here the pulse width will be smaller, width means this Tp. Now, you are actually modulating that Tp. Okay. So, that is something we are doing. Over here the amplitude is lower, so probably the pulse width will be little higher, and over here amplitude is even lower, so pulse width must be even higher. Then again it is becoming smaller. As it goes up, probably the pulse width becomes, means of course we should have same amplitude now. It is almost like now frequency modulation. Okay. So, the amplitude of the pulse remains similar, it is just the width you are modulating, the width of the pulse. Okay. And the other thing is the pulse position modulation, which is almost like a phase modulation. So, basically you position your pulse depending on the amplitude of this particular thing. So, basically whoever will be having higher amplitude, probably they will be closer to the this pulse starting time. Okay. So, what will happen if we just draw that at this point, because the amplitude is higher, so pulse will be closer to that pulse starting time. At this point, because this is lower, so this will be further away, the pulse, now the width will be same, amplitude will be same, it is just the position of the pulse which is being varied. Here it is more negative, so it will go much more away from the this one, again it will come closer, so something like this. Okay. So, this is called pulse position modulation, this is called pulse width modulation, and this is called pulse amplitude modulation. Okay. So, this is something which we will be trying to employ. Okay. So, let us now try to see, as we have said that before we do this, we need to have a mathematical foundation of this pulse modulation, so that we can analyze their characteristics and everything else. So, that signal processing part of that or probably the signal analysis part of that has to be dealt first before we even jump into these modulation techniques. Okay. So, if you just see, we have probably discussed this, what is actually a pulse modulation. So, in pulse modulation, what you are trying to do, suppose I have a message signal. So, whenever we could have actually transmitted this message signal, okay, that is without modulation we are transmitting it. Now, instead of doing that, probably I will have some theoretic foundation that not all the time, because this is a continuous time, continuous amplitude signal. Okay. So, this is time and this is amplitude, it might be voltage, it might be whatever it is, so whichever parameter we put for this. So, that is taking any value and also the time every time the signal exists. So, if some theory can tell us that probably for this signal description I do not need all the time, so I just need some portion of that time to define that signal, or maybe some discrete values of time where that has to be just defined. Rest of the time I do not have to have definition of this signal, and I can still reconstruct the signal as it is. If we can do that, then probably we will have some modulation format which is similar to pulse modulation. So, in the pulse modulation, basically what we are saying is in discrete time. So, time actually we are making it discrete. in discrete time we are trying to get the signal and send the signal, send some part of the signal. Rest of the time we are keeping it open where others can modulate. So, it is also a multiplexing scheme, like in frequency FDM we have told that in frequency domain we can multiplex things. This is actually where in time domain we can multiplex things. So, that is called TDM. So, we will discuss more about it later on, but that is what we try to do, that time domain can we actually discretize it and only take discrete time events or time samples to represent the whole signal. So, that is what we are now targeting. Later on, when from here we will be transiting towards more of a digital transmission, what we will do, we will not only discretize the time, we will also try to discretize this vertical axis. So, then our amplitude also will be having discrete values and we will take those values and represent them in a digital format. So, that is actually what is termed as digital transmission. So, that is why I told that this is one step ahead towards digital communication. So, you are just discretizing or trying to discretize the time or trying to free up the time that you do not use it for whole time to represent the signal. So, that is something we will try to now theoretically analyze. So, this was first done by Nyquist. Most of you must be knowing about Nyquist sampling theorem. So, that is something we will try to demonstrate now. Okay. So, what is Nyquist sampling theorem? That actually tells that if I have some trains of impulse function or delta function, so which looks like this. So, this is a periodic signal where at a particular interval, let us say that is Ts, I put a delta function. Okay. So, this I represent as del Ts t, okay, which is nothing but a train of delta function. So, we can write this as delta t minus n Ts, where n goes from minus infinity to plus infinity. Okay. So, this is just at different location in time there are delta function, okay, and it is a periodic one. After every Ts it gets repeated. So, the basic signal is something like this, from minus Ts by 2, sorry, minus Ts by 2 to plus Ts by 2. This is just a delta function and it is defined from here. This gets repeated. Okay. So, basically that is the train of delta function, and sampling theorem says, see, we have already told that we want discrete values of it. So, sampling theorem says that we multiply these two. So, whenever we multiply with delta, if you multiply, what happens? It just picks that value at that point wherever that delta is defined. So, it will be actually picking those samples at those delta locations. So, the output will be something like this. If I just draw the envelope, so this is where one delta. So, at that point delta of the strength which is following this GT will be captured and so on. Okay. So, this I can write as delta t. Okay. So, what is this? This is nothing but our GT multiplied by delta TST, right. So, this original function multiplied by this train of delta function. If we just multiply these two, we get a sampling. Okay. So, sampling is nothing but we are discretizing in time. So, basically we are picking that sample value at that location and then ignoring all others between this Ts. And again at the boundary of Ts we are picking another sample value which is having amplitude exactly equivalent to that at that point whatever GT has sample value or amplitude value. So, it is just picking those samples. So, we have got our representation. So, this is actually a sampled version of our signal. Okay. Now, let us try to see what happens in frequency domain. So, that is what we want to understand. So, this GT, what is the corresponding frequency domain representation? what we are saying is this GT has a frequency domain representation of GF which looks like this, which is defined from minus let us say B to plus B. So, eventually we are saying the signal we are sampling, that is a band limited signal and a low pass equivalent signal. So, it is a low pass band limited signal having maximum bandwidth or maximum frequency component up to B. So, it has a bandwidth of B. Okay. So, that is the GF, that is the Fourier transform of that particular signal. Okay. Now, if we wish to do Fourier transform of this one, what we know it is the Fourier transform of this, Fourier transform of this, and because they are multiplied in time domain, it should be convoluted in the frequency domain. This is something we know. So, first we already know the Fourier transform of this GT. So, we need to understand what is the Fourier transform of this del TST. That is something we will have to first do. Then only we will be able to characterize the Fourier transform of that G hat T, okay, or G bar T. Okay. So, this del TST, what is this? This is actually, this looks like this, it is a periodic signal with this as being repeated every time with a period of Ts. So, therefore, I can represent this as a Fourier series. So, if I can do that, so what I can say is it is actually summation n equal to minus infinity to plus infinity, okay, dn e to the power j n omega s t, where omega s is just 2 pi by Ts, or I can write it as 2 pi Fs, okay, where Fs is 1 by Ts. Okay. So, I can, from my Fourier series understanding, I know that any periodic signal can be written like this, where what is dn must be calculated as Fourier has said for Fourier series analysis. So, that must be integration over the period, which is minus Ts by 2 to plus Ts by 2, and then we have to multiply with the function itself, which is delta t. So, delta t into e to the power minus j means n omega s t dt, right. That should be my dn. What is this? It is delta t multiplied by this, that must be at t equal to 0, whatever value of this is there. So, that is 1. So, 1, now you integrate this. Okay. So, basically what will happen, if we have also seen the property of delta t, if it is integrated from minus infinity to plus infinity with a function, it will just give me as output the value at 0, whatever it is, right. So, delta t if it is multiplied by a function and then integrated over the entire duration, I will be getting this particular function. So, if I integrate it from minus Ts by 2 or from minus infinity to plus infinity, because delta t is 0 anywhere else. Okay. So, I can always write that as if it is integrated from minus infinity to plus infinity, and then I will be getting at t equal to 0 whatever value I do get. Okay. So, that should be what I was telling, that at t equal to 0 whatever this value, that should be the value. So, e to the power 0, that is 1. So, it must be 1 by Ts, right. So, dn becomes 1 by Ts. So, it is not a function of n anymore. So, it is independent of n. So, I can actually take this outside the summation. So, what I can write, this delta Tst I can write as 1 by Ts, because I can take it outside the summation, summation n minus infinity to plus infinity e to the power j n omega s t, right. I can write it this way. What is the Fourier transform of this? Let us say that is del Ts f. This will remain the same. It is a summation of exponential. Each exponential, if I take Fourier transform, what it creates? It creates a delta function in the frequency domain at that location wherever it is. Okay. So, at that frequency location. So, basically this will be just a sum of delta function. So, this happens to be this is something we already know, that if I have this means I can get a time period accordingly, which is 1 by means 2 pi by Ts. This can be represented at Ts, it will be creating delta. This is something we have already known. This is the relationship, Fourier conjugate relationship, e to the power minus j 2 pi fst will create a delta function at fs. Okay. So, this I already know. So, it will be just a summation of delta function, that is very good. Now, I need to find out this g bar f, which is gf or maybe capital Gf convolution of this, which is 1 by Ts summation n minus infinity to plus infinity delta t minus n Ts, right. I can write it this way. Now, the convolution is a integration and this is a summation, these two does not depend. So, I can interchange them. So, g f I can take inside, there is no problem in that, because this summation has nothing to do with f. So, I can write this as 1 by Ts summation n minus infinity to plus infinity, this is nothing but gf convolution delta, sorry, this should be, that is a frequency domain representation. So, that must be f, right. So, that is f minus n Ts, oh, sorry, I have done a wrong thing. This is actually, if I am putting it at f, it should be n fs, okay, where fs is 1 by Ts, right. So, that is the Fourier representation, right. If I put it in omega, it will be n omega s, okay. So, that is a wrong thing I have done. So, that must be fs, okay. So, this is what we are getting. Now, we know anything convoluted with delta must be giving me the same thing at where the delta is, okay. So, the convolution theorem with respect to delta, this will give me Ts summation n minus infinity to plus infinity, this will be just g f minus n fs, that is what happens. So, just that g goes into every fs. So, in frequency domain, what will be the corresponding representation if I just try to see. So, that was my gf, now I am trying to get this g bar f, right. So, how that will be represented? This is, this entire thing gets repeated at every fs. So, this is 0, at fs also this will get repeated, at 2 fs because n goes from minus infinity to plus infinity. So, at 2 fs also this gets repeated. So, this is fs, this is 2 fs and so on. What is the strength of them? So, the strength should be this 1 by Ts. So, that must be the strength. So, this should be 1 by Ts and this Gf gets repeated everywhere, even in the negative side also. This will be at minus Fs, I will have that same repetition, right. So, I will have this repetition from minus infinity to plus infinity. Now, the thing is that if I wish to keep the signal intact, that means after doing this I can still reconstruct this signal. How in the frequency domain, if you see how I can reconstruct this signal, if whenever I am shifting this, if the fs is chosen carefully so that this and this are separated, they are not overlapping. So, you can immediately see if my fs is too small, suppose I put fs over here. So, what will happen? This is getting repeated and this is getting repeated. Now, these things are getting superimposed. So, if fs is small, then I will have problem. So, what should be my optimal fs so that I can still separate them out with a low pass filter? That is all I will have to do, right. So, for that, what is this point? This is fs plus b, sorry, this is plus b just, and what is this point? This point is fs minus b. So, I need to ensure that fs minus b is greater than plus b. So, I need to just ensure this fs minus b is greater than plus b, or fs must be greater than 2b, that is the famous Nyquist theorem. So, as long as whatever the bandwidth of the signal, if twice that, if I means twice of that which is 2b, I do my sampling frequency, that means I choose my Ts in such a way that my sampling frequency, which is 1 by Ts, that becomes bigger than this 2b, I am fine. I know that I can put those samples and then I can transmit it. Those samples, if I just pass through a low pass filter which has a bandwidth of b, it will be able to trace that signal back. So, I can reconstruct that signal, I am not losing any information. So, I can still recover that signal back. It is only when this condition is violated, I know there will be a superimposition and my sampling is not giving me very nice reconstruction of the signal. This is quite obvious. Suppose I have a signal something like this, okay, and then if I just take the samples like this, what will happen if I try to reconstruct without knowing what has happened inside. So, I will just reconstruct it this way, right. So, it will take out all the variation, whereas if I start getting samples like this, it will capture the entire variation. So, basically Nyquist criteria tells me that at least what should be the what should be that Ts, what should be that value. So, from here I can calculate 1 by Ts must be greater than 2b, or I can say this Ts must be less than 1 by 2b. So, that is the maximum value of Ts, 1 by 2b. I cannot really go beyond this. If my Ts becomes more than 1 by 2b, I will be losing some of the information. So, my sampling will not be good representative of my signal. So, as long as I am, while sampling I am considering this, I know that the sample will be a true representative. So, this was the sampling theorem which has given a huge impetus for modulation, because with this only we know that probably the entire time domain I do not need. I can just pick some discrete values of time where I represent the signal, and that is good enough. Okay. So, what we will try to do, we will come back and try to see, yes, they are good enough, those samples are good enough, we will try to show that theoretically.